460 terawatt hours.
Yeah, that is just...
I mean, that is the projected global electricity consumption for data centers in the near future.
Right.
And if we look at the trajectory that the International Energy Agency is charting right now, we are on pace to essentially double that by 2030.
Which is, I mean, it's just a staggering number to even wrap your head around.
It really is. And we all know, the main driver here, it's the massive scale out of artificial intelligence. But we rarely talk about the actual physical wall that kind of power consumption hits.
Because, well, you can only pump so much current into a square foot of silicon before thermodynamics just takes over entirely.
Right.
We are watching the industry approach this hard physical limit where you simply cannot push enough electricity through a server rack to feed these GPUs without literally melting the infrastructure.
Yeah.
The resistance is just too high at that point.
Which is exactly the focus of our deep dive today.
Okay, let's unpack this. We are looking at a fundamental rewiring of the physical internet and AI infrastructure as we know it. Yeah, rewiring is the perfect word for it.
Because the major players are effectively stripping out traditional copper electrical traces and replacing them with like,
right,
which is this technology called co-packaged optics, or CPO, alongside silicon photonics. And I was going through some of the recent supply chain breakdowns from places like TrendForce, reading the analyst notes from Webull and Counterpoint Research, and even the technical specs from companies like Lightmatter and SK Hynix. And it's clear this isn't just, another upgrade cycle.
No.
It's basically a rescue mission for Moore's Law.
It really is. I mean, to understand why the shift to light is mandatory right now in 2026, you kind of have to look at how data actually moves inside a switch.
Okay, break that down for us.
So for the longest time, we've relied on traditional pluggable optical transceivers. So you have your massive switch ASIC in the center of the board, and the data travels electrically across the PCB, across the board to the edge of the box. And that's where it hits the pluggable module and gets converted into light to travel down a fiber.
Right, and historically that worked perfectly fine. But an electrical signal is basically just pushing electrons through copper.
Yeah.
I always think of it like trying to force high-pressure water through a pipe that's just packed tightly with sand.
That's a great way to look at it, yeah.
There's immense friction.
Oh, yeah.
And as you crank up the speeds to, the hundreds of gigabits per second that modern AI demands, that electrical signal degrades terribly over just a few inches of circuit board.
Exactly. The signal attenuation is just brutal. So to compensate for that, that sand in the pipe, you have to blast the signal with power.
You have to push harder.
Right. You need heavy DSPs, digital signal processors, and retimers just to clean up the degraded signal before it even reaches the optical converter at the edge of the board.
Wow.
And all of that takes massive amounts of electricity, and all of it generates a ton of heat.
So silicon photonics is the equivalent of replacing that sand-filled pipe with just a hollow glass tube.
Pretty much, yeah. You'd shine a flashlight, and the photons just travel with near-zero resistance.
And that brings us to co-packaged optics, right? If the electrical journey across the board is the bottleneck, CPO solves it by essentially eliminating the journey entirely.
Right, you just cut it out.
You take the optical conversion engine and you park it right on the exact same substrate as the central ASIC.
Yep.
So the data barely has to travel, millimeters electrically before it becomes light?
It's just millimeters, yeah.
I saw a note from TrendForce looking at Broadcom's 51.2 terabit Bailey switch, and because they are using this CPO architecture, they're seeing a 70% reduction in power consumption for the optics compared to traditional pluggables.
70%, and a 30% reduction in the total power draw of the switch itself.
That's incredible.
And when you multiply that across an AI factory with, thousands of switches, you are saving megawatts of power.
Right, which means you can power more GPUs instead of just powering the networking gear.
Exactly. And we are way past the theoretical stage here. Storage Review just confirmed that Nvidia's Spectrum-X Ethernet Photonics platform has actually hit full production.
Oh, wow. Full production already.
Yeah, and they are achieving 5 times lower power consumption. But the metric that really stands out in their data, what's fascinating here, is the reliability.
Really?
Yeah, they are claiming a 10 times higher MTBI, which is mean time between incidents.
Okay, let's unpack that reliability metric because the Storage Review data noted the Spectrum-X platform uses 4 times fewer lasers. And I know in a massive data center, the lasers themselves are usually the first thing to die, right?
Oh, absolutely. They run incredibly hot. The heat degrades the semiconductor materials, and they just fail.
And if a laser fails, that optical link goes down, and suddenly your multi-million-dollar AI training cluster is just sitting idle, waiting for data.
Yeah, precisely. So by moving to CPO and ditching the discrete pluggable modules at the edge, Nvidia drastically reduces the total laser count across a fabric that spans hundreds of thousands of links.
I see.
You remove the discrete DSPs, you reduce the component count, and the overall system reliability just skyrockets.
Okay, but I have to challenge the logic on the heat aspect, though.
Sure.
Because if the lasers are the primary point of failure, specifically because they are highly sensitive to thermal degradation,
Yeah.
taking them from the edge of the board and co-packaging them millimeters away from a 1,000-watt network,
Yeah.
ASIC seems totally counterintuitive.
It sounds crazy, right?
Yeah, I mean, you were taking the most heat-sensitive component and literally gluing it to the hottest piece of silicon in the room.
Mm-hmm.
How does that not just instantly fry the optics?
Well, that is the core engineering tension of the decade, honestly. And it's why this rollout hasn't just happened overnight. It's a massive thermodynamic puzzle.
So how do they fix it?
The way they are solving it, or, attempting to solve it, is by decoupling the light source. Many of these CPO architectures use an external laser, small form factor pluggable module. They call it an ELSFP.
ELSFP, got
Yeah,
it.
so they keep the actual laser diode on the front panel where it's cooler and can be, easily replaced if it dies.
Right.
And then they run a blind optical fiber into the CPO module on the ASIC. So the module next to the hot chip only handles the modulation and detection of the light, not the actual generation of it.
Ah, okay. So you pipe the raw light in from the cooler edge, you do all the data encoding right next to the processor, and then send it out.
Exactly.
Okay, that makes a lot more sense. And it really gives context to the architectural roadmaps we're seeing right now.
Yeah, it really does.
Looking at Counterpoint Research breakdown of NVIDIA's rollout, it's a very calculated, phased approach.
Mm-hmm.
With the current Blackwell generation, they're heavily relying on CPO for scale-out networks. So connecting different racks together using their Quantum X800 and Spectrum X800 switches.
But notice how the strategy fragments as they move to the Vera Rubin platform, which is entering production this fall.
Right, the new platform.
Yeah, the scale and density just changed the physics again. For their scale out, they are actually leaning into linear pluggable optics, or LPO.
Okay, what is that?
So LPO keeps the pluggable form factor on the edge, but strips out the power-hungry DSP. It relies entirely on the switch's internal SerDes to drive the signal, so it saves power, but it limits the physical reach.
But for the scale-up network on Rubin, which is, how the GPUs talk directly to each other inside those massive NVL576 pods,
Right.
they deploy CPO, they use OSFP XD ports and passive optical fiber. Because when you were trying to make a 576 GPUs act like a single unified brain, latency is everything.
Everything, absolutely.
By pulling the DSPs out of the optics and handling the conversion via CPO at the switch, you avoid the processing delay and the thermal load of active transceivers entirely.
And the volume projections for this are steep. I mean, the analysts at Webull are forecasting NVIDIA's Spectrum X shipments alone at around 15,000 units for 2026.
Okay.
But they project a jump to 100,000 units in 2027. It is a completely parabolic curve.
Here's where it gets really interesting, though. Because even that 2027 volume is just transitional when you look at what Counterpoint outlines for the 2028 Feynman architecture.
Oh, yeah. Feynman is wild.
The Feynman is where we hit true gigawatt-scale AI factories.
Oh.
And they are completely abandoning the external switch for the scale-up fabric.
Right.
They plan to put native CPO directly onto the GPU package itself. They are aiming for pods of 2,304 GPUs.
It's massive.
You literally won't have electrical networking leaving the processor at all.
Yeah, they are building a system of systems. But what's highly strategic about Feynman is their approach to standards. NVIDIA is, notorious for proprietary tech like NVLink.
Very true.
But with Feynman, they are expected to adopt the OCI, the Optical Compute Interconnect Multi-Source Agreement, for these optical modules.
Interesting. So they are opening it up a bit.
Right. They keep the NVLink logic layer proprietary to maintain their ecosystem dominance, obviously. But by using standardized physical optics, they de-risk their own supply chain. If one optical vendor has a yield issue, they can source from another without redesigning the entire pod.
Which is a very real fear, because moving this technology from, lab samples to millions of units is exposing some terrifying bottlenecks in the global supply chain.
Oh, absolutely.
TrendForce highlighted 3 major choke points that the industry is slammed up against right now.
Yeah, the first being the optical engines themselves. We talked about external lasers, but integrating the modulators, the waveguides, and the detectors into a single silicon photonics die requires highly specialized wafer fabrication.
Right, because they're essentially manipulating light, not electricity.
Exactly. Most traditional CMOS foundries are set up to print logic. Etching silicon waveguides requires a level of sidewall smoothness and precision that is entirely different from printing a standard transistor.
And that leads right into the packaging bottleneck, which is arguably the worst traffic jam in the tech world right now.
Oh yeah, packaging is a nightmare.
CPO directly competes for the exact same advanced packaging capacity TSMC that the AI GPUs themselves need. We're talking about TSMC's CoWoS and CPO technologies. I mean, you are already space-constrained trying to interpose high-bandwidth memory next to a logic die.
Right.
Now you want to add highly delicate optical dies to that same microscopic interposer.
It creates an incredibly fragile dependency chain. Storage Review actually mapped out the specific 5-vendor relay race Nvidia has to use just to build one of these CPO switches.
5 vendors for one switch.
Yeah, so TSMC handles the base fabrication, then it goes to Spelea for the advanced chip-scale packaging.
Okay.
Then Lumentum has to provide the indium phosphide laser chips, TFC Communication builds the subassemblies, and finally Foxconn handles the system-level assembly.
Well, wait, think about the yield risk there. You have an AI ASIC that costs tens of thousands of dollars.
Yeah.
Right? And you permanently attach these microscopic optical engines to it using an ultra-expensive packaging process.
Huh.
If there's a single defect in the silicon photonics, say, a modulator fails a testing parameter after it's packaged.
Yep, you're done.
You can't just unscrew it. You have to throw away the entire fully functional multi-thousand-dollar logic chip.
Yeah, and for a long time, that yield loss was the primary argument against co-packaged optics. The math just didn't make sense. You were tying the fate of your most expensive silicon to the lowest yielding component in the package.
But the industry's finally solving it. I was reading up on a startup called Light Matter, and they just unveiled something called V-Click.
Oh, V-Click is fascinating.
It is the industry's first detachable fiber array unit for CPO. The mechanics of this are brilliant. It allows manufacturers to test the optical engines independently, verify they are known good, and early then attach them.
And critically, it survives the packaging process.
Yes, the mold and grind compatibility. When you package these advanced chips, you encapsulate them in an epoxy resin and literally grind the top down to expose the copper pillars.
Yeah, it's a violent process.
Exactly. You obviously cannot have delicate glass optical fibers attached during a brutal mechanical grinding process.
No, they'd snap instantly.
Right. But with V-Click, you do all the harsh packaging and grinding first, and then you literally just plug the optical array into the finished package. And they are claiming less than 1.5 decibels of insertion loss, which means the physical alignment of the light is incredibly precise.
And insertion loss is the silent killer in silicon photonics.
Real.
Yeah, when you pass light from a glass fiber into a microscopic silicon waveguide, if the alignment is off by even a fraction of a micron, the light just scatters.
Oh, wow.
You lose signal power, and that's your insertion loss. So achieving sub 1.5 dB on a detachable, pluggable interface at this scale is a massive engineering feat.
And it requires precision manufacturing that doesn't really exist at data center scale yet, which is triggering some pretty wild pivots in the broader hardware market.
Definitely.
I was looking at a financial report from Big O Finance covering Largan Precision.
Oh yeah, Largan?
If you don't know Largan, they are the undisputed king of smartphone camera lenses. Like, if you have a high-end phone in your pocket, they probably made the lens.
Right. They are huge in consumer tech.
But their CEO, Lin Ping, just announced on their earnings call that they are pivoting hard into AI infrastructure.
Which is wild.
Right. They're currently sampling fiber array units and have made it their second highest business priority. A consumer smartphone tech company jumping into the deepest end of data center plumbing.
But it actually makes a lot of sense if you think about it. The alignment precision Largan has perfected for multi-element smartphone cameras is exactly the discipline needed to align glass fibers to silicon waveguides.
Ah, I see.
Though even Lin and Ping admitted the technical barriers are brutal. They can't just retool their iPhone lens machines, you know. They are custom building entirely new equipment. And they are targeting mass production for 2027 or 2028 because it simply takes that long to stand up the fabrication lines.
And we're also seeing companies like FOCI scrambling to deploy highly automated production lines for 1.6T and 3.2T FAUs by the second half of 2026.
Right.
The entire supply chain is realizing that this optical transition isn't just some niche networking upgrade, it is the fundamental foundation of the next decade of compute. The margins are irresistible.
It's the classic picks and shovels play during a gold rush. But, the shovels require submicron laser alignment.
Exactly. And you can see this financial ripple effect hitting the massive incumbents, too. Look at the memory market.
Oh, yeah, memory is going crazy right now.
High bandwidth memory, or HBM, was the first major physical bottleneck of the AI volume, and the companies that solved it are printing cash. A breakdown on Moomoo highlighted that SK Hynix is generating so much profit from HBM that they are reducing their share count by up to 10%.
That's insane.
Yeah, that's a 40 trillion won, or roughly $29 billion program. And Samsung is looking at a shareholder return package over $100 billion.
But they aren't just buying back stock. They see where the bottleneck is moving next. SK Hynix knows that pumping data out of the HBM and into the GPU electrically is going to hit that exact same thermal and power wall we discussed earlier.
Right.
So they recently published a highly detailed roadmap in the journal Nature Electronics, outlining their move to photonic interposers.
Literally putting the memory itself on an optical network.
Exactly. They are researching how to bypass the electrical traces entirely and link the memory stacks directly to the compute units using light.
Wow.
Because if we connect this to the bigger picture, they understand that the silicon photonics market today looks exactly like the HBM market looked 3 years ago.
Meaning what, exactly?
Meaning it is defined by extreme scarcity, immense pricing power for the very few who can actually manufacture it, and massive capital expenditure requirements.
So what does this all mean? The market sizing data supports that completely, by the way. Mortar Intelligence has the silicon photonics market expanding at a 27.19% compound annual growth rate.
That's a huge growth rate.
It is.
Yeah.
They projected jumping from just under $4 billion in 2026 to over $13 billion by 2031.
Yeah.
But what stood out to me in the Mortar report is that the sheer volume of AI investment is essentially subsidizing this technology for everyone else.
Right.
Because hyperscalers are throwing billions at solving optical yields, silicon photonics is getting cheap enough and reliable enough to bleed into adjacent industries.
Yeah, we're already seeing it in telecommunications, actually. With 5G front-haul upgrades, you need high bandwidth, low latency optical links to connect the cell towers back to the base stations.
And automotive applications, too. Level 3 autonomous driving relies heavily on LiDAR. Companies like Aurora are deploying FMCW, which is frequency-modulated continuous wave LiDAR, for long-range sensing on semi-trucks. To make FMCW work at a commercial scale, you have to integrate the lasers, the modulators, and the photodetectors all onto a single silicon photonics die.
Oh, wow.
So the exact same optical integration techniques being funded to keep AI servers from melting down are being put into autonomous vehicles to help them see the highway at 70 miles per hour.
It's the normalization of a bleeding-edge science. I mean, a decade ago, co-packaged optics and silicon photonics were mostly relegated to, academic papers and lab demonstrations.
Yeah.
Today, they are the critical path to building gigawatt AI factories. Tomorrow, they are the invisible infrastructure powering our cars and our mobile networks.
So to recap the ground we've covered today, we are hitting a hard thermodynamic wall with traditional copper networking. The power required to drive electrical signals at AI speeds is totally unsustainable. Nvidia, Broadcom, and the hyperscalers are aggressively moving to co-packaged optics, bringing the light directly to the processor to cut power consumption by up to 70%. We're watching the supply chain completely reorient itself, from TSMC's packaging lines all the way down to smartphone lens makers like Largan.
Yeah.
And they are all racing to solve the submicron alignment and yield issues.
And we're seeing the capital from the AI boom fully fund the maturation of silicon photonics, turning it into a foundational technology for the broader tech sector.
But I want to end on a detail from the Mortar Intelligence report that really highlights the physical knife edge this industry is walking right now.
Okay.
We talked earlier about the external lasers solving the heat generation problem. But the optical engines themselves, the silicon ring resonators that actually modulate the light inside the CPO module, are incredibly sensitive to heat.
Right, they're very delicate.
Above 70 degrees Celsius, these resonators experience severe thermal drift.
Ah, I see. The physics of the silicon literally changes.
Right. A single degree of temperature fluctuation changes the refractive index of the silicon, which alters how the light behaves inside the waveguide. It detunes the signal.
That's a huge problem.
So as we build these gigawatt AI factories and demand more and more computational power from the GPUs, driving ambient temperatures higher and higher, we really have to ask, are we just trading an electrical wall for a thermal one?
It's a fair question.
By packing these hyperfragile optical resonators millimeters away from the most powerful silicon on Earth, are we racing toward a brand new physical limit that even light cannot bypass?
That is the multi-billion-dollar question the material scientists have to solve before we hit 2028.
It really is. Thank you all for joining us on this deep dive. Keep questioning the infrastructure that powers our future, and we'll see you next time.